right, let's go ahead and get started. If you want to hang out for a few minutes before you go, I'm going to hand your test back. Also, I extended the web work for section 2.7 to Sunday night, I think. If you haven't looked at that, I would definitely recommend looking at it sooner than later. There's a lot of tricky stuff on that. I've had a lot of questions about it. I would be very shocked if anybody got to the end of that without needing help from somebody. So please look it over as soon as you can, and yeah, let me know how I can help, or yeah, use that ed discussion board on Canvas. I don't think anyone's gone there yet, but that's a good place to kind of crowdsource for help. Solomon? Yeah. Oh, you want the title? Yeah. Sorry. So chapter 3, all about inverse functions. Specifically, we're going to talk about exponential functions first off. Any questions about anything before we get going? All right. What is an exponential function? What's that? On the input. With exponents on the input. Can you give me an example?
Like 3x squared.
Okay. Do we agree with that? That this thing right here is an exponential function? Everyone's in agreement? Okay. Any other examples you can throw at me?
So the seventh.
So basically, things that look like this. You know, so constant base, variable, sorry, no. Variable base, constant exponent, could have some kind of coefficient. These are, so we're in agreement that these are what exponential functions are? Yeah. All right, I hope you're not too married to that idea. So let's talk about what they are. So those are polynomials that you just threw at me, like those like kind of power terms, the bases and the variables in the base and the exponents are all constant. Typically what exponential functions look like are, so probably see this, hopefully you see the difference here. So where's the variable in that thing there? The variables in the exponent, the base is constant. So this is what an exponential function is by definition. So when you hear someone say that, you know, you probably heard the phrase in all areas of your life, something grows exponentially, which people don't usually mean that. You're just usually saying that it's growing at a fast rate. But what exponential growth really is, you know, I'll give you an example here. Let's say this is y equals 2 to the x. Every time x goes up by 1, my function will do what?
So like 2 to the power of whatever it goes up by 1.
So
Times itself by 1 more.
By not quite. I mean, you're kind of describing what squaring is, right? Or like what x to the power of something would be. But like, let's say x can only be integers. What are the first few values of y? 1, 2, 4, 8.
Just multiple.
What am I doing every time?
Doubling.
I'm doubling, right? And that's kind of what exponential growth is. As your input grows by 1, you're growing by some like multiplicative growth factor. In this case, I'm doubling because that base is 2. So hopefully you see the difference between what y'all told me what an exponential function is and what I'm saying it is. I mean, x squared does not grow that way. You know, 1, 4, 9, 16, that is not, there's not some constant multiple I can bring in to get the next values every time. So what's the domain of this thing? And by the way, I'm saying A is any number that's positive, but not 1. Garrett? Or it could be any real number, right? There's no way to really violate this thing. So the domain is in interval notation, negative infinity to infinity. What is the range? Is there a maximum? Like, for example, if I keep doubling, am I gonna get like a ceiling? Like, am I gonna get like a top number? No, that's not gonna happen. So I think I can say that my range is, without bound from above. But the trickier thing to see is what happens on the lower end. Is there a minimum value I can reach? Those of you who are saying yes, what do you think it is? Go ahead.
One.
One? Can I go lower than one?
0 to 1 and then 1 to infinity.
What's that?
And then the limitation 0 to 1 and 1 to infinity.
So I can't, so you'll do it can equal one?
Is that one alone?
Well, y equals 2 to the x, I think that can equal 1, right? What x value would give me 1?
0.
0. So then it doesn't even matter what the base is, right? Anything to the 0 will be 1. So we know we can go as low as 1. Can we get values that are smaller than 1?
Oh. The base could be 0.
No, this time I want the base to be positive. Oh, remember, what did we say that x could be? Garrett?
It's angle below 0.
So it can be any, I could give you any positive number here. So I can get as close to 0 as you could possibly want to, but I cannot reach 0. I think I'm going to guess that maybe we're assuming that x had to be positive, or at least non-negative, but
It's negative, it's still a good fraction, right?
if it's negative, then this becomes like 1 over 2 to the power of something, right? Which is always going to be definable, but it's always going to be positive. I can make it as small as I want to. I can't ever make it 0 though. Does that make sense? Go ahead,
So
Solomon.
part of the exponent laws would be is that b greater than 0, is that just saying it has to be positive, right?
Yeah, I haven't brought in B yet, so I got other bullets here. These things, hopefully you can tell me what's going on here. A is a constant. Can I rewrite a to the x plus y? This is something you always do, just probably kind of as a snap judgment thing now, but maybe you don't.
Like each move in front of the, like multiply a by x and y.
Not multiply a by x and y. I saw your hand up.
Is it a to the x times a to the y?
Yeah, and usually we go the opposite way.
Mhm.
But if you have like x to the third times x to the ninth, what's that equal to? X to the 12th, right? So knowing you can add the exponents, and then similarly, what's a to the x minus y? A to the x over a to the y. How about a to the x times a to the x to the power of y? A to the xy. Now I'm bringing in b. Can I rewrite that into something? Not even really simplify. It's not going to be simpler necessarily, but is there any other relationship you can think of there?
A to the x times b to the x.
Yeah, you can think about. I mean, I don't want to use the word distribution because that's not really what's going on here. But yeah, you can just apply that exponent to both your bases. So any mystery here, I think you've probably seen these a lot. Not so much in this class, but previously. So again, letting f of x be equal to a to x, a to the power of x. Let's look at some limits. What's going to happen to this function as x gets really, really big? It's going to get really, really big, right? So yeah, it's going to get really, really big. Is it going to get limited by anything? Nope. So long as a is greater than 1, this limit's infinity. What if we go really far left? What if x goes to negative infinity? Limit's going to be 0, right? So this is, in the case of this, you'd be looking at, 1 over a to the x. So are you okay with me substituting this limit here? The limit is x goes to infinity of 1 over a to the x. Do you believe me that those two limits are really looking at the same thing?
Yeah.
So yeah, so if you divide a constant one by something that's just going to grow, it's always going to be positive, but I can make it as small as I want. All right, now let's talk about a being a positive number that's not quite as big as 1. Now what's the limit as x gets really, really big? Still goes to infinity? Let's someone give me an example of an a I could use here.
0.5.
0.5 sounds good. So 0.5 to the power of x. If x is 0, what's that equal to? How about x is 1? Yeah, half, 0.5. If you square it, 0.25. It's so what's happening? It's decreasing, right? So what's going to happen is I let x grow to infinity. It will never reach 0, but it will tend towards 0. I can make that as small as I want. What if I let x get really, really small? Or go to really large negative numbers? It's going to have the opposite effect. Because now, by the same token, I can substitute this limit for this one. As x gets really, really big for what other function? Not 0.5 to the x, but what?
2 to the x.
Be 2 to the x, right? How'd you get 2?
Because 1/2 reciprocal is 2.
Right, there you go. Basically, you're looking at 1 over 0.5. So really that you're looking at a reciprocal relationship from these bullets to these. How we doing? Okay. All right, so let's evaluate this limit. As x goes to infinity of this function here. Anybody have any thoughts? Should we look at some x and y values? When x equals 0, y equals 2. How about 1? 2?
Is the limit going to approach 0 as it approaches infinity?
Maybe. What do y'all think? So yes, the limit of this function as x gets really, really large is 0. One other thing I want to point out about kind of the definition of exponential functions. What did I multiply this number to get this number? 1/5, right? Is that also true here? Would that be true all the time? Yep. And then that's what I'm doing, right? I mean, I had my starting with this value of 2, basically just multiplying it by 1/5 to the power of whatever my x dot is. So yeah, that limit is, that's going to eventually just shred to 0, get as small as we want. Any questions? Go ahead.
So x in this case is 1/5. Is the thing the same as 2 to the 1/5? Or no, I guess it's growing.
So x is a variable, right?
Okay.
If you want to put it in the language of, so I think what I threw at you before was this, right? F of x equals a to the x.
Yeah.
This is that's kind of incomplete for this one here, because I should really say this: f of x equals a times b to the x. So in this case, then what are like a and b? Garrett?
A is 2, B is 1.
Very close. I agree with a is 2 as well. Yeah, I'll call it 1/5. mean, what Isabel said is also true. I could call it 5 to the power of negative x, which would be the same kind of thing, but basically, this 1/5 is kind of like, that's that exponential growth rate. As x goes, if x grows by 1, your function is going to, weird to say grow, but it's going to grow by this multiplicative rate of 1/5. How we doing? Has anyone ever seen this weird thing before?
Yeah.
So what's this limit? So why do we say 1?
The 1 over x is going to approach 0.
That's going to approach 0, right? So it looks like it should be 1 because the inside of this thing is going to go to 1. But couldn't you also say that it's going to just keep getting larger because I'm raising these numbers to just bigger and bigger powers?
It's adding.
So which one of those is going to win, right? So either, it's kind of strange, right? Because, yeah, 1 to the power of anything is 1, right? But anything raised to bigger and bigger powers just grows forever, right?
Because it's like you say, like even if you put like 1,000,000 x, it'd be 1 plus 1 over 1,000,000.
Yeah, so yeah, it's a really big power, but it's a really small, it's a number that's very close to 1, right? So kind of a weird limit to think about. The thing that it actually approaches is this, it has a limit, and it's this weird 2.18728, I mean, this non-repeating weird decimal that shows up so often that we give it a name, and that name is E. Have we seen this number before? Okay, this is where this number comes from, is this seemingly arbitrary exponential function and letting x get really, really large. Another way you might see this is the limit as x goes to 0 of 1 plus x to the power of 1 over x. Which is kind of asking the same thing. As x gets really, really small, the inside of this will go towards 1, right? But this will be getting very large. Good.
So on the calculator, when you do e to the x, that's essentially plugging in, the calculator plugs that in for you. Plugs in that.
No, that's a good question. So E itself
Is the
is this limit.
Oh,
So if you just took your calculator and did e to the 1,
Mhm.
you would get this number.
okay.
So the reason that your calculator, like e to the x on your TI calculators, the graphing ones, e to the x is really hard to find, really easy to find. It's not easy to just ask for an e, like it by default wants an exponent. And that's because so often when you're dealing with exponential growth, this number e just like pops up. So I'm guessing most of you have seen this number before, but this is really where it comes from. It's by definition comes from this limit. But we're going to use it for lots of stuff in this class and beyond. But like this is a very common base for exponential functions. So let's look at this limit here. The limit is x approaches infinity of e to the 2x over e to the 2x plus 1. Any thoughts about what this thing should do? Get smaller? How come?
Because it's 2 equivalent values for like e to x, but it's just adding 1 on the bottom.
Okay.
The number on the bottom will be bigger.
So do you think the limit exists?
It has to be 0.
So I got to vote for 0 because the thing on the bottom is bigger. Isabel?
I never mind, I'm thinking through this.
Okay. Got a thought? 0.1? How'd you get 0.1?
I don't know, I mean, I'm guessing.
Okay. No, I mean, I'm not, yeah, so when I ask you how you got your answer, I want to know. I'm not like trying to penalize anybody by any means. Solomon?
Could it maybe not exist, because say like it was like dividing, and you could just cancel out e to 2x, it would be nothing. It would be 0 on top. So. Never mind.
Okay. So I mean, we really would love to have a way to come at this systematically, right? But we're all everyone's doing right now is guessing so far, which is what I was hoping would happen, which is so fun. You right?
Isn't it just one?
Why do you say one?
Because since they cancel out, it's 1/1 plus. Like, it's just 1/1.
Can I really cancel them out though?
No, this is a plus.
So yeah, I mean, I can't like mathematically cancel them out, but I think I know what you're saying. Quinn?
Is it like for approaching one? It's like eventually it'll get so large.
It's forever approaching one. So what would the limit be then? That would make the limit one, right? So let's think about it. I mean, I would love to have a way to get at this using, techniques we have. Can I use the limit laws on this thing? Can I break it apart?
Yeah.
So what's the limit as, so let's just look at the numerator by itself. As x goes to infinity, what is e to the 2x doing?
Increasing.
Increasing to what? So I can't use the limit laws because
That's be definite limit.
I have to have all the little limits exist. But is there anything I can do to this that make the limits exist? Because we've done this in the past where we've looked at like rational functions like this. If you have x squared over x squared plus 1, what's that limit? That limit's 1, but you can't use the limit laws on that. Do you remember what we did before to make the limit laws accessible to us?
Rearrange, like, would that turn into?
Oh, it was so long ago. I can divide both numerator and denominator by x squared. And doing that will give me this new limit of 1/1 plus 1/x squared. Do those limits all exist? Clearly the ones do, they're constant. What's the limit of 1/x squared as x goes to infinity? 0, they all exist. So could I do something similar to this guy to make those limit laws something I can look at? Garrett? Divide the top and bottom by e to the 2x. So let's see what happens when we do that. What does the numerator become? Numerator becomes 1, that limit clearly exists. How about the denominator? 1 plus 1/e to the 2x. Does that limit exist? Just the 1/e to the 2x part? So you have, you have 1 divided by a thing that's just going to keep growing. So that will be 0. So because of that, I can use my limit laws here. This becomes 1/1 plus 0, which is equal to 1. So I did have a few people who were kind of reasoning to, well, the top and the numerator and denominator kind of they're not the same, but they're going to be growing at the exact same rate. So because of that, that limit ends up being 1. For the same reason, we think about this polynomial here, and it's like not the most mathematically rigorous thing to think about it this way, but you have the x squared numerator, x squared denominator, they're going to grow at the same rate, right? Which means the 1 is going to get overwhelmed. Just for the same reason, the 1 in the denominator of our function here is going to get overwhelmed by e to the 2x. So I don't believe we'll ever achieve a value of 1, but we'll get as close to it as we would like to.
What value you summon for on like the word 1/e to the 2x? What value you summon to 0?
Not really subbing in, because you can't really sub in infinity because it's not a number. What
But yeah, as it gets larger and larger.
we're really thinking about here is, so I have a fraction here. The numerator is constant. The denominator is just going to get as large as you want to make it, which means the overall term will get really, really small. Eventually trending to 0. Any questions there? All right. How about this thing? E to the 7x sine x as x goes to negative infinity. What's going to happen here? Can I use the limit laws? What's that? If I wanted a derivative, I could do product rule, but I can't. That won't necessarily get me to a limit. Isabel?
I don't know because we have the X in a changing position of its polynomial. So it's just gonna keep on growing and growing.
What's going to keep on growing and growing?
Well, our E7X is gonna keep on growing and growing, and so that's.
I'm actually not sure the e to the 7x part is just going to keep growing. So what do I want x to do here?
Approach negative infinity.
Approach negative infinity. Garrett?
E to 7x just approaching 0.
So that part itself, I'm going to write that down. So the limit as x approaches negative infinity of e to the 7x, that is 0. Good.
And since it's 0, isn't the final one just 0? They're multiplying together.
Only if both the limits exist. So what is this limit? The limit as x approaches negative infinity of sine of x. Yeah, that doesn't exist, right? So it doesn't exist. So we can't use our limit laws the way it is, but what does sine of x do as x, like if I let x go into these big negative numbers? Does it get really big? Does it get really small? How does it behave? Go ahead.
So they just like oscillate between 1.
Just oscillate between -1 and 1, right? So I'm going to bring up something that we did a while ago. We can use the squeeze theorem here. I heard groaning. Nobody likes this thing. I don't know why. But one thing we do know about sine of x is this is always true, right? -1 is less than sine of x, which is always less than 1.
Has to be between the entire whole E7, E7X sine of X.
Yeah, so we care about e to the 7x sine of x, right? Before I go any further, I should make sure that everyone is buying into this idea. So now what I'm going to do, I'm going to multiply all 3 branches of that inequality by e to the 7x. So remember the way the squeeze theorem works. If these 2 things have the same limit, what happens to this one?
It's the same as
It's in between them, so it has to have the same limit too. So let's make sure that happens. What's the limit as x approaches negative infinity of negative e to the 7x? And what's the limit as x approaches infinity? No, negative infinity of e to the 7x. We already wrote down that one 0, right? So then what's the limit of the other one be? -0. And it's just. It's the exact opposite, so it better have the opposite limit. So because of that, what's the limit of the thing I really asked you about? Must be 0 by squeeze through. So squeeze theorem is a really kind of bulletproof way to show that this limit is what it is. But I like the way that, a lot of us started thinking about it. We know that e to the 7x is going to go to 0, right? And we know sine, that limit doesn't exist, but it's also bounded. So you have something that's going to 0, and you have something else that's, while its limit may not exist, it's at least kind of contained, right? So hopefully that limit of 0 is, hopefully we believe it. Any questions here? All right. And that is it for 3-1. So let's dive into 3-2 for a little bit. So let's talk a little more about inverse functions, specifically logarithms. Are logarithms things that people have looked at quite a bit at all?
Yeah.
They're somewhere in the memory banks? Okay. Come on. All right. What is an inverse function? What does that mean?
Or like opposite slope?
Not necessarily opposite slope. Depends on what you mean by opposite. So if a function has a slope of 10, what does the inverse function have a slope of? Okay, so no, that's not necessarily going to be true. Go ahead.
Well, it's just the inverse of any function is just the replacement of the x and y.
Right. So inverse means like, I've drawn all these block diagrams on the board of, here's a function f, and if x is a thing that goes into it, that what comes out is called f of x, right? If this function has an inverse, it does the same. It's the same process in reverse, right? So x goes into this thing. This is still function f, right? But if I do this, what comes out? Not f of x, but something related to it.
Why?
What was that?
Why?
Kind of. We want to represent it in function notation, so yeah, it could be y. But this thing is f inverse of x, because we're doing the same, like following all the same rules and processes of whatever f is. So, for example, if f is the square root function, then 16 goes in. What comes out? 4. But I want to go in the reverse now. So 4 goes in. What comes out? 16, right? So what kind of function is f inverse? It's not a log. What's the inverse of square root? Square root. So I'm still using what f does. I'm just doing the inverse process of it. I'm doing whatever undoes f. Anything else we remember about inverse functions? What kinds of functions have inverses? Because it's only a specific kinds of functions.
Exponentials do.
Exponentials do, but why? What's special about them?
They're exponential.
Go ahead.
It's because they have like asymptotes, like they approach certain values.
They approach certain values, so those are functions that typically have inverses. I'm going to throw a phrase at you that's probably from your past. Hopefully, you're not too distant past, but one-to-one functions. So a one-to-one function, by definition, is, so let's say I have two x values that are different. If your function is one-to-one and I give you any two different x values, that means the y values are different. that means that by definition, this has to be true. F of x1 is different from f of x2. So in other words, a one-to-one function never has the same value twice. For every unique x value, you get a unique y value. And you can think of lots of things that are functions where that's not true. A really simple example would be like f of x equals 2. That's not one-to-one. Every single x value in the world gives me y equals 2. So it is a function, but it's not one-to-one. Hopefully sounding somewhat familiar. So let's talk about a few. Is the function x cubed one-to-one? Never. Let's think about it. So you said, so Solomon thinks it's one-to-one. Jarek thinks that you have a negative value and the corresponding positive value.
Are one-to-one functions and linear functions the same?
Almost all the time. Let's talk about that. Are linear functions one-to-one? What's the only exception? I actually said it right. The constant, the horizontal line, right? Horizontal lines are linear, but they're not one-to-one. But if you have a line that has a slope of anything that's not 0, it's absolutely one-to-one. So what is -1 cubed? -1, what's 1 cubed? 1. So can't prove by example, but I will tell you that x cubed is one-to-one. If I can convince you with a graph, this function kind of looks like this. So maybe another way to think about one-to-one functions that's a little bit different from the way that we just talked about. If I give you a y value, you'll always get a different x value. So no matter what y value you start with, if you go backwards, that always maps to a different x value. And hopefully that'll be more clear when we talk about this function. How about f of x equals x squared? Is that one-to-one?
No.
I see some head shakes, I hear some no's. All right, prove it to me that it's not. Just give me 2 and -2, and that is enough, right? That is enough to prove to me that this is not one-to-one. So you gave me 2 x values that delivered the same y value. So this kind of function is not invertible, but x cubed is. Any questions on the distinction between the two? And just because I did in the last slide, if you have the graph of something, what's the kind of test that you? A vertical line test for a function, right?
Yeah.
Does this thing pass that vertical line test? So what's the corresponding test that goes with one-to-one functions? Horizontal line, right? And that's why it works, because if I have a single y value, I better only get one x value that corresponds to it. In this case, there are infinite numbers of y values you could pick that have 2 x values that map it. But
So the one-to-one is just when every x value has one y.
that's why it's called one-to-one. Yeah. One x value goes to one. One x value goes to one y value. That's just what makes a function a function.
Yeah.
It's the other way that's one-to-one. For every one y value, there's only one x value. Any other questions? All right. So let's talk about some consequences of inverse functions. So f is a one-to-one function, has a domain A and range B. So this f to the -1 thing, how is that related to f? That's the inverse, right? So there's these two different functions are related in a very specific a way. What is the domain of F inverse? What's that?
It's a range of function.
What is that in this case? B. So I believe it was, actually, I'm not sure who said it here, but when you have an inverse function, you're taking X and Y and you're exchanging them. Typically, we think of X as the domain, Y as the range, but you're just exchanging them, right? So the range of F inverse is what? Yeah, by definition is A. If I'm telling you that F of X is equal to Y, then what is something I could say about the inverse that corresponds to that? Go ahead.
Y is equal to, or f of y is equal to x.
Yeah, close. F inverse of Y is equal to X. So yes. If I have a point on, if I have some mapping from the function and I know the inverse exists, then I, just as it's been said, the domain and range have been exchanged for one another. How we doing? So given F of X equals X to the fifth, find the inverse. I'm gonna go ahead and give you for free that this function is 1-to-1. Do you remember how we find inverses, Isabel?
Oh, I was gonna.
Oh, go ahead, Ben.
I was gonna say, can you make like a general rule that exponents that are 1-to-1 and exponents that are even?
I think that's fair. So yeah, and the real reason that is that even roots can be, they're always positive, right? They exist, which is what makes them not 1-to-1. So how do we find inverse? Is this something you remember?
So just put y type x.
Right, and that goes back to the idea of when we're inverting, we're just exchanging the domain for the range, right? So if I have this function, y equals x to the fifth, in the function f, x is the input, y is the output. But in this new function, I want x to be the output, right? So I would like to solve for x. So how would I solve this thing for x?
Just the fifth root of y.
Take the fifth root of both sides. So that gives me x equals the fifth root of y. So I'll say this, f inverse of x is equal to x to the, I'll keep it in the root form, the fifth root of x. Right?
Is it always the same thing, because like right at the beginning, you just change x and y?
Yeah, that's fine. I do it at the end, it does not make a difference. So I want to verify that I actually, I'm pretty sure I did that right, but we should verify it. So how do we verify it? So basically what I have going on here is I have x going through some function f, and then it's going to come back through f inverse, right? So x is going to go through a function and have a bunch of stuff done to it. Then it's going to go back through the inverse and have all that stuff undone. So what better come out after we've gone through both steps? Whatever went in, right? So because of that, I should be able to do either one of these things. Compose the inverse with the function, or compose the function with its inverse and wind up with x, right? So let's make sure we can do that. F of x is x to the fifth, right? So I want to put the inverse, the fifth root of x raised to the power of 5. Does that come out to x? Absolutely. So that function is, the inverse we found is correct. Any questions there? So I have a function with a domain and range, A and B. I know a few things about that function. I'm telling you the inverse exists. Can I find those values? Can I find F inverse of 5, F inverse of 2, and F inverse of 7? What is F inverse of 5?
3,
Why?
because you're just switching the X and Y, so then it's just whatever the original input was, is gonna be the output of the
Right.
inverse.
So this all comes from the idea that I told you F of 3 was equal to 5. So if the inverse exists, yeah, the inputs and outputs get exchanged. So by the same logic, what is F inverse of 2? And 7? Can I say anything else? Like, what's F inverse of 3? So it might very well exist. I have, I can't even be sure that. So is 3 in the domain of F? There's no way to know. Sorry, no, sorry. We do know this. Is 3 in the domain of F?
Yeah.
It is,
Yeah.
because like, I defined it. Is 3 in the range of F? We don't know. There's no way to know. So all I know about this function is it's got those 3 points. It might not even have any others, but I just haven't told you. So yeah, there's no way to say anything else about other inverses or other values of this function, unless you learn more about it. Any questions so far about, hopefully shake off some dust of what you know about inverse functions and exponentials? All right, I'm gonna go ahead and stop here. You're free to go unless you want your test back and hang out, and I'll get them to you. Otherwise, I'll see y'all on Monday. You keep it.